Hello class, this is Ms. Friggins with today's video on section 9.2, Sum and Difference Formulas for Sine and Cosine. As you're watching the video, please remember to write down notes, including important information, statements, equations, formulas, or graphs. Feel free to pause, rewind, or replay the video as often as you need so you can get a clear understanding of what's occurring in the video. And at the conclusion of watching the video, submit that summary as well as an top question via the online list form about what happened in the video. All right, let's begin. We're going to work with the sum and difference formulas for sine and cosine, identities that you are responsible for knowing and memorizing. So I'm just going to give them to you right out here, right out front, so you can see what they are. Sum and difference, sine of sum, sine difference, sine cosine sum, cosine difference, okay? Sum meaning adding, difference meaning subtracting. And I'm going to prove all of those using that same triangle that we talked about. Well, I'm going to prove some of those using the same triangle we talked about earlier last week in class. Okay, so as we can see here, we have this alpha plus beta right triangle with a hypotenuse of 1. And if I want to find the sine of this angle, then all I have to do is find the adjacent side and divide it by the hypotenuse. Well, the adjacent side, as you can see, is made up of two parts. The adjacent side is made up of the sine alpha, cosine alpha, which is this part. And then it's made up of the cosine alpha, sine beta, which is this part. Okay? And that's how we get that sine alpha plus beta. Similarly, we do the same thing with the cosine of alpha plus beta. And that's equal to the whole length of AC minus the length of AB. And the length of AC, the whole thing, is cosine alpha, cosine beta. And the length of the piece that we subtract from it is this sine alpha, sine beta. And then tangent alpha plus beta looks a little bit different because we actually used it with tangent of 2 beta. But if I just have alpha and beta and I want to get this ratio of opposite over hypotenuse in terms of tangent, then it's just involving some algebraic manipulation. I'm not going to go through each step by step, but I am going to show you how it works. So feel free, if you don't understand, to take a look and see the algebra that was used to come up with this answer. And feel free to push pause. Okay. Now, I know some of you are saying, okay, that's this sum formulas for sine and cosine and tangent, but how do we prove and understand that for the difference formulas for sine, cosine, and tangent? Well, we're still going to use our alpha and beta triangle, but we're going to rearrange our alpha and beta triangle a little bit differently, okay? So in this case, here's our alpha and beta triangle. Except that even though they share the same side length for their hypotenuse, I've rearranged the triangles a little bit differently. And I want to introduce this third angle called C. And the thing about C is that A plus C is 90 degrees, which makes sense because if we're in a right triangle, then the other two angles have to be 90 degrees, as we can see here. All right. But if we arrange it such that the right angles are like this, then we have something which is a rectangle which has 4 right angles. So if these angles are right angles and this angle is a right angle, then it makes sense that this side right here, this angle, is also a right angle. Okay? And in order for it to be a right angle, then that must mean that this piece right here must be A, because A plus C is equal to 90 degrees. And if this piece right here is A, then the question is, what do we call this piece right here? Well, this, if you said correctly that it looks to be A or alpha minus beta, you're absolutely correct. It's alpha minus beta. So now we have an alpha minus beta right triangle where the hypotenuse is 1. And as you can see, since the hypotenuse is 1, then this side length, this vertical side length, is really the cosine of alpha minus beta. And this horizontal side length, because it's across from alpha minus beta, is equal to sine of alpha minus beta. Okay? Well, why is that important? Well, that proves the rest of the sum and difference formulas, as we can see, because Since sine of alpha minus beta is opposite over hypotenuse and the hypotenuse is 1, I need to come up with an expression for this side besides sine of alpha minus beta. And what I do know is that this side is the result of taking this original side length, sine alpha times cosine beta, and subtracting this side length, which is cosine alpha minus sine beta. And what I'm left with is just this sine alpha minus beta side. And the same thing for the cosine of alpha minus beta. It's equal to this side length, which can be represented by adding up two pieces, which is this piece, which is cosine alpha cosine beta, and this piece, which is sine alpha sine beta. Okay, and that's why they work. And we can do the same thing to prove the tangent difference formula, but in the interest of time, we're going to move on. Besides using the sum and difference formulas for proving identities, we can also use the sum and difference formulas for calculating cosine and sine values for angles that are not special right triangle angles. How can we do that? Let's look at an example. They say find the exact value for cosine of 15 degrees. So let one angle be 45 degrees. Let theta be 45 degrees and let phi be 15 degrees. Okay. So cosine of 15 degrees is the same thing as cosine of 45 minus 30 degrees, okay? And using the sum and difference formula, in this case, the difference formula for cosine, the difference for cosine values would be equal to cosine of 45 degrees times cosine of 30 degrees plus sine of 45 degrees times sine of 30 degrees. And some of you may be saying, oh, well, we already know what those values are. And we do know what those values are because they are special right triangle angles. And we can evaluate the cosine of 15 degrees without using a calculator, just by using the special right angles of 45 and 30. Oh, I'm sorry, they messed this one up. Okay, that was a typo. Phi should be 30 degrees. So sorry, I don't know why. I guess 15, 30. Okay, so anyway, moving on. So that's one way we can use the difference formula for cosine to find the exact values of cosine of an angle without having to use a scientific calculator. And you can check your answer in a calculator by saying, what is cosine of 15 degrees? It is square root of 6 plus square root of 2 over 4, which is approximately 0.9659. Okay. Now we can also use the identities to actually prove other identities. And earlier we had a problem in our GA, which involves sine of 3 theta. And some of you didn't know how to solve that algebraically, and now we're going to give you the tools to do that. So we use the sum formula for sine, and as you can see here, it's like this. And now we can use also the double angle identities for sine of 2 theta. And the double angle identities for the cosine of 2 theta. And the idea is to get it in terms, and then we have something that looks like this. And then that's one way to write sine of theta, 3 theta, in terms of just sine and cosine of theta. Okay. All right. And I think that's it for that example. Now I want to show you something about the graph. So suppose, let's take a look at sine of t plus cosine of t. When I graph the function sine of x plus cosine of x, it looks very much like a sinusoidal function. The only difference is it seems to be not to have an amplitude of 1 because this high value here is above 1. And it seems to be some type of shift because, as you remember, sine and cosine, sine is 0 at 0 and cosine is 1 at 0. So this doesn't look exactly like a sine or cosine function, but we do know it is a sinusoidal function. So let's can we represent sine of x plus cosine of x in terms of just a sine or a cosine? And we can. And the reason why we can do that is this basically looks like a shift of pi over 4 to the right of the cosine function. So what I'm going to do is, okay, very quickly, I'm sorry, I misspoke. If this is the sine function, then I move it over to the left, pi over 4, to get it to this type of situation. Okay, so this is like basically saying this is a horizontal shift of the translation of the sine function. And we use the sum formula of sine, and we get something that looks like this. Okay. And then we know what cosine of pi over 4 is and what sine of pi over 4 is. And so then we represent that as, and we multiply both sides by the square root of 2. So we get that the square root of 2 of sine of t plus pi over 4 is equal to sine t plus cosine t. And to see if it matches, I plug this into the graphing calculator, and as you can see, it matches perfectly, both of them. Okay. All right, moving back on. So that's another way you can use the sum and difference formulas to actually graph the function in terms of sine plus cosine function in terms of just sine. All right, some of you may be asking, well, what if they have the same amplitude? Can we do that? And you can using these formulas. And because in the interest of time, I'm just going to show you it and not talk you through it. If you have questions, you can ask me about it as well. In this case, we're introducing u and v so that theta and phi can be represented in terms of u and v. Theta is u plus v divided by 2, and phi is u minus v divided by 2, and we end up with something like that. Okay. Oh, I also forgot. Let me see. Did I forget? And here's an example as well. Okay, just so you can see. All right, I didn't want this to be too long. Oh, I also forgot down here, sorry. Going back to this problem, I'm so discombobulated, sorry, my parents are here. So how can I rewrite this A1 sine B2 plus A2 cosine B2 in terms of just sine? And the idea is in order to do that, we need to know what A is, big A is, as well as what phi is. Okay, what's the horizontal shift and what's the new amplitude? This is the derivation of how we can determine what big A is and phi is using little a1 and little a2. And we do that basically using this, that A is equal to the square root of a1 squared plus a2 squared. And if you don't understand, look at that. And then phi can be formed by the inverse tangent of a2 over a1. And then this is the example here. And we did an example where A1 and A2 were 1 and B was 1. And that's how we ended up with our square root of 2. 1 plus 1 is 2. And we ended up with pi over 4 because the tangent of the tangent of 1, inverse tangent of 1 is pi over 4. All right, sorry it took a little bit longer than I wanted it to be, but I wanted to get this to you by Saturday morning. Thanks.